Hey there, welcome back to ECE 382. We're moving on to Module 7, Finite State Machines. We're going to review finite state machines, what you saw in 281 last year. We're going to then apply it to our line sensors, specifically the two middle sensors, to create a driving robot that can follow a line. So just going over a little bit of review of finite state machines. Remember, finite state machines include inputs, outputs, states, and transitions. And depending on what kind of finite state machine, depending on the inputs, we transition states, and depending on the states, we provide different outputs. So that's the definition there, and we'll go through this a little bit later, of your Moore machine. And then the Mealy machine, again, remember, is the one where we transition. The output depends on the transition. So we're going to look at both of those a little bit in detail, and then also look at how can we code this in C. The thing to note about a state is that it's what we know about the current conditions, or the current, what we believe to be true currently. So for example, with our robot, that could be, in the current state we are stopped with two line sensors off the line and we are lost. That would be a current state, what we know about the current conditions. And then dependent on different inputs, so now we're talking physical inputs, we could change the states. So maybe the robot gets a bump and now it's ready to go again. And that's what we'll see today in the lab next time, is the robot's going to drive until it hits a bump, and then once it hits a bump, it's going to be waiting until another bump occurs, then it'll drive again. So all these different inputs, physical inputs, whether it's the reflectance of the line sensor or the bump sensors, are going to change the states, and then that output, which is going to be the motors, is going to be what drives us forward. So let's take a look back to EC 281. I know this is mid-corona, COVID, going home, so a lot of this might be review, or it could be something that you've forgotten since then. But let's just think of the simple vending machine that only takes quarters and sells Monster drinks, because it's my favorite drink. Does not provide change, and one Monster is 50 cents. There's one input, a coin, and then one output, the drink. And this state transition table and state transition diagram, the diagram should look very similar to what we saw last year. So we have 0 cents, we put in 0 coins, we're not going to provide a drink. We provide 1 coin, we transition over to the 25-cent state, which we're going to call state 1, which still does not provide a drink. So there's no output here. Again, this is a Moore machine because the output relies only on the state and does not rely on the input as well. And then we go to coin. We're going to switch over, we get 0 coins, we stay there at 25 cents. We get another coin, we go over to 50 cents, and then we can provide a drink, 1 Monster, and then we're going to just automatically go back to our 0 state. And then we provide that ghost state, which allows us to then fill in our 4 different states. This state inputs, it's going to be 2 bits, right? Because there's state 0, 1, 2, and 3. So we need to fill in that ghost state so that we make sure we have all 4 states accounted for. What you'll learn in this class, and when it comes to application, ghost states aren't as important. We're not going to program a bunch of ghost states because if you think about it, say we expanded this, we're only going to use 2 line sensors. We're going to use the 2 middle line sensors. So we're not going to use, the 3 over here, and we're not going to use the 3 over here. But if we did extend this to all 8 line sensors, you'd think there would be a lot of states, and if we didn't care about them all, that would be a lot of ghost states we'd have to program. So it's not quite as important in this case. But just remember back from EC 281, we did have the ghost states, so we're just going to keep that included. Something new that's included in this state transition table is this delay. And when we're talking with physical systems, it's really nice to provide this delay so that states don't change too often because of noise. And think about this, like we throw in one coin, there's no way another coin could get in within 2 milliseconds or 2,000 milliseconds or 2 seconds. Well, I guess that's 2 seconds. So potentially you could get another coin in there within 2 seconds. But say this was 2 milliseconds, that coin, we would not be able to get another coin in there. And so we'd want to make sure that when we put that one coin, the sensor doesn't think there's multiple coins going in. So we provide this delay, and that allows us to kind of ensure that noise doesn't affect our system. So delay ensures noise doesn't affect our system. This is really important with real-world sensors. And we don't want our robot to make choices too quickly. So for example, if it thinks it's left of the line and then we start moving right to try to get to the center of the line, it's going to take some time for us to get to the next state. And so we don't want the robot to automatically switch to a different state too quickly before the motors can react. The motors are going to be pretty slow compared to the reflectance sensors, so this delay really allows us to ensure that our motors have time to react before the noise of the system does too much, or from the sensors. So this table just corresponds directly to what we saw before. You're at 0 state, we have 0 coins. Input is 0, then we stay at the 0 coin state. If there's a input is a 1, then we go to the 1 coin state, so on and so forth. Should all be very much review from last semester. But now we're going to take a look and see how do we take this state transition table and diagram and correlate that to C. Specifically, we're going to stick with pointers. This allows us to kind of access our memory a little easier. So you guys all took Comp Sci 210, so you know all about pointers. But let's take a look at our state transition table and how we represent that in C code. So the first thing we are going to do is we're going to define our different states here: 0 coin, 1 coin, ghost, 2 coin. And each of these 4 states here are going to be a representation of our enumerated type down here, our FSM. So our FSM, let's start down here first. Actually, let's take a look at our state. What does our state include? So our state includes 3 different variables. So it includes an output, it includes a delay, and it's going to have a pointer to the next state. So think of this as our little arrows here. So how many, there's 2 different bits here. So there's going to be 2 choices for each of our different states to transition. So each of these states should have 2 different transition possibilities. This one having don't care, so both of those would go straight back to state 0. So we'll create a little array here that's going to represent our states. I'm just going to shift that over a little bit. Running out of room. No, thanks for nothing. There we go. Oh, we lost a little bit. It's okay, it happens. Probably would have been easier just, oh my gosh. Technology gets you sometimes. Alright, random 3 over here. Can't erase it, it's going to stay there. Ignore it. Alright, state. There's a lot of work. And it's a pointer to our next state array, which is going to have 2 bits. Or sorry, 2 different indices. And those are all semicolons for our struct. And we're good to go. Alright. So that's going to be our state representation. So each part of our enumerated type is going to be, so this is going to be an array of states, and our enumerated type state, which includes our output, our delay, and our next state. Okay, so those are our 3 different parts of our struct, our enumerated type. Let's take a look at what our different states are going to be. So these are going to be pointers to this state table representation, our finite state machine representation. So this one here is just a pointer to our first state, our zero state, our first state, and then second state and third state. And so each of these 0 coin, 1 coin, ghost coin, 2 coin is going to represent a different indice in our struct, or our FSM array here. So this FSM array is an array of states. So we have our first state, and we look at the order here. So we have output, delay, and the next state. So if we are in state 0, our 0 coin, and we go back and look at this table right here, this state array is going to be an exact copy of this table here. So let's draw a cool little arrow. These correspond exactly. So we take a look at our 0 coin state. That's going to be the first one in there. Our output for that is going to be 0. Our delay is 2000. And then we're going to have our array of next states. So that's this array right here. And we have our 0 coin. And our 1 coin. And that's our first index into the FSM array. So that's just one of our states. And you can see now why we need another squiggly bracket. And you can see now here why we're using an array. So this array here is going to actually just point back to our FSM. So say we're in state 0, right? We're in state 0 here. Our output's 0, our delay is 2000, and if our input is a 0, we're just going to go straight back into our 0 coin state. And if it's a 1, then we're going to shift over to our FSM index 1, which is our next state. So output is still 0, 0. If we look exactly at the table, we're going to copy it verbatim. 1 coin, and then our 2 coin, if our input is a 1, and that is our second index. Third is our ghost state, which again, output 0, 0, delay 2000, and then we have our 0 coin and 0 coin because we're going to go back to 0 no matter what. Then last but not least is our final state. The output for this one is a 1, so and then our still delay is 2000, and this time we're going to go to 0, 0 again, and we are done with our finite state machine array. So this array here, the FSM array, just represents this table exactly. That's a key thing to note. And FSM array copies state transition table exactly. All right, and then each of these, so it's an array of states. Those states, again, that's our enumerated type we created, has an output, a delay, and a next state. And these next states, we could just this could just be ampersand FSM0, the address of FSM0, but that name doesn't mean anything, so we're using the 0 coin state, and then we're defining that as a pointer to our 0 index. So these 4 guys here are just a way for us to have meaningful names so that we can transition appropriately. All right, so that's just representing the data structures for our FSM. So now we need something called the engine. So the FSM engine, which is you can think of as the controller, which is going to allow us to go through these states. So we built the structure of the finite state machine Now we need to actually transition through the finite state machine. And we're going to use pointers. So we're going to have a pointer to the current state. Let me get back to my red pen. All right, we're going to have our input and you can think of this input in this example as just going to be a button press. So I'm programming this as if we really could implement this on the MSP 432. So this isn't just fake code. Well, this part is fake since I didn't write the vending machine init. All this would be similar to do. This would be the vending init is just kind of the idea of initializing the pins like you did with the reflectance sensor. So that's where we would initialize our input and initialize our output, which would be an LED, which will be illuminating every time we're giving a drink out. And then we're going to set our initial state. So we're going to set the pointer equal to our 0 coin state. So that's our initial state. All right. So the first thing we want to do is we want to figure out, so our output P1 out, which is going to point to, this is going to point to one of the LEDs. So we're going to say, so the first thing we do is we clear the bit of interest. So 0x02, that is pin 1, 1, right? Because 0x01 would be pin 1, 0. 0x02 is pin 1, 1. And we are going to clear it. So we're clearing the bit right there of interest. And then we're going to set it to whatever our output is. So PT is our current state. Output, that's going to give us this output right here. And if we look at our FSM for our 0 coin state, that's a 0. So we're using our pointer and we're getting the output to that current state, which is a 0 in this example. Then we're going to delay, just make sure, yep. Now we can delay, and we're going to delay in milliseconds, right? Because our table says it's in milliseconds. So we have a convenient built-in function, clock, delay 1 millisecond, and we're going to take our current state, and we're going to take the delay that our current state has. Then we need to get an input from our, so let's get the input, which is either going to be a 1 or a 0, because it's just a switch. And we're just selecting the bit of interest. And so whatever pin 4, the input of pin 4 bit 1, we're going to set that to the input. So we're going to get pin 4, 0, sorry, this is pin 4.0, and that's going to, we're going to see what that value is, and we're going to set that to the input. And then we are going to set the next state. So we're going to take our pointer and I'm going to set it to our pointer next state array input. So this, oops, this is exactly just going to take our, so our current state, which say we're still in that 0 state. If the button is pressed, that's a 0 to represent 0 coins. Or sorry, if the button is not pressed, that's a 0 to represent 0 coins. So we're going to go into our next state array, which is this guy right here. and we see that the not pressed is a 0, so our next state is going to turn into 0 coin. If it was pressed, our next state would turn into 1 coin, and our pointer would point to that appropriately. And that will help us to control through this finite state machine. And that's it. This is the exact same thing you would do for any finite state machine that we're building in this class. The lab, what we're going to do in the lab is we're going to build the data structures up here, and this is already built for you. But we'll go through that, and we're going to have some information about this on the pre-lab for next time. So once we finish the lab, you'll have looked at this, and then the pre-lab is going to test some of your knowledge for lesson 7 or 8. Sorry. All right. So last thing to cover, again, this is review. We're looking at the Mealy versus Moore machines. I just want, because this is so important, just to bring it back. Output. So Moore machine output value depends on current state. The significance is the state. So we care all about the state. Input tells us when to change the state. Output tells us what to do while in a state. Okay, Mealy, a little bit different. Output value depends on input and current state. Significance is in the state transition, because that's where our output occurs. Input still means when to change state, but our output now means more of how to change the state. All right, that's enough for this video. Next time we'll go over the exact example that we're going to see in the lab, but this gives you a good review of finite state machines, and then how do we apply that to C code.